work done by a spring force. The spring force. We see a spring stuck attached, a block attached with. This shows a spring in its relaxed state. That is, neither compressed nor extended. It's natural length. An axis has been placed parallel to the length of the spring with the orange x0 at the position of the free end when the spring is in relaxed state. What is relaxed state? Neither compressed nor extended. Remember, x0 is at the relaxed state. It's not the length of the spring, okay?
Energy can be stored in many ways. Compressing a spring, for example. We'll use this glider floating on an air cushion to show just how much energy is stored in a spring for a given amount of compression. This arm attached to the glider will compress the spring contained inside this glass tube. To determine how the energy stored in the spring varies with different compressions, we will compress the spring by 3 different distances and then use the energy stored in the spring to launch the glider up a tilted track. The spring energy will be converted into kinetic energy, then into gravitational potential energy, which is directly proportional to the height of rise of the glider. We launch the glider with the spring compressed 1 unit, and it rises up the track 1 unit as measured on the bottom scale. If the spring is compressed 2 units, how high will the glider rise? If the compression is increased 3 units, how high will the glider rise? The energy stored in a compressed spring is proportional to the square of the compression distance.
When a ball bounces after being dropped, it will not normally bounce higher than its original height. When we drop this object, it bounces higher than its original height. How can we explain this behavior? The object is a handball cut in half. Before it was dropped, it was flipped inside out, storing energy in the elastic material. When the half ball hops back to its normal shape, it has enough energy to go higher than the original height.
Many forces in nature have the same mathematical form as the spring force. That's so crucial. To a good approximation, for many springs, the force F extended by the spring is proportional to the displacement D of the free end from its position when the spring is in relaxed state. F equals minus kd. K is larger than 0. This is a Hooke's law. We look at this one. This is a natural relaxed state. We pull it, it has force this one. We push it, it had a force this one. K is the O's negative direction of displacement. F equals minus kx, Hooke's law. The minus sign of the Hooke's law indicates that the spring force is always opposite in direction from the displacement of its free end. You put it x, displacement is d to the right, and the force is to the left. If we push the spring, the displacement is into the left, and the force against you is to the right. It's always opposite in direction. The constant K is called the spring constant and is a measure of the stiffness of the spring. Note that a spring force is a variable force because it depends on the position of the free end. F can be simplified as Fx as a function of x. Work done by a spring force F equal minus kx. This is work done by the spring. Since it changes, so we can divide it into many small sections. Each section is the work dWi, and then we put them together. Okay, and this Fx is minus kx. So we put minus kx inside and change this to integration. This becomes integration Fx dx from xi to x final. From initial position to the final position. Fx equal to minus kx. We put this one inside, and this is a very simple integration. We get this is half kx final minus half kxi. So this is positive, this is negative. Look at this one. It's all square. If the x final equal to xi, for example, you push this xi, you put it up, x final. Even the length of the spring is different, but this is equal, so the work done by the spring is 0. If the final length from the free end is smaller than initial length, the work done is by the spring is positive. Vice versa. X final larger than x initial, the work done by the spring is more than 0. Work Ws is positive if the block ends up closer to the relaxed position than it was initially. It is negative if the block ends up farther away from x0. It is 0 if the block ends up at the same distance from x to 0. When they equal, it might not equal. When it is positive, when the negative, okay, they might not be the same. So usually when the xi is 0, starting from the relaxed state, this is 0. So we get the work done by the spring is minus half kf final squared. The work done by an applied force in the spring case, we know delta k equal to k final minus k in equal to two forces. Applied forces, spring force. So do work 2. If the kinetic energy change is the only change of the energy. If V final equal to Vi equal to 0, all stationary at t equal to 0 and t equal to t final, then we find this is 0. And we find the work done by an applied force equal to minus work done by the spring force. If a block that is attached to a spring is stationary before and after the displacement, then the work done on it by the applied force displacing it is the negative of the work done on it by the spring force. Sample. In the figure, a chromium canister of mass m 0.40 kilogram slides across a horizontal frictionless counter with speed v equals 0.50 meter per second. It then runs into and compressed a spring constant K 750 Newton per meter. When the canister is momentarily stopped by the spring, somewhere here, but what distance d is the spring compressed? We'll find the compressed distance. It's very easy work. We see that the work done by the spring is minus half kx squared. We put it to the top. This is the distance d equal to half kd squared minus. And this one should equal to the kinetic energy change. The finally is stopped here. Initially it has vi, v squared. So we put this one inside, we say these are the same thing. We equal these two, we find V. D squared equal to m over kv squared. So D, you put the number inside, you get a number. It's about 1.2 centimeter.